Hello, well we've come into school to do a wee experiment. Remember this place, look. Sad. Anyway, we'll be back soon enough. Right, what was I going to show you? This is moment of inertia. I have here 2 metre sticks and they are exactly the same mass. They've got little masses attached to them. I'll show you this, they're taped on. And it's just these standard. Can I show you? There's one there, right? There are 400 grams taped on that end and 400 grams taped on the other end. And then another metre stick that's exactly the same, but there's 400 grams taped closer to the middle and 400 grams taped closer to the middle. So those 2 metre sticks are identical masses. Therefore they have identical weights, I suppose, but it's the mass we're interested in. So 800 grams on each of them, plus the mass of the metre stick if you like. But here's the thing, they have identical masses. If I wanted to rotate them though, I'm going to show you this. There's the one with the masses close to the middle, right? If I want to rotate that with my hand, if I just rotate that back and forward, that's dead easy. Nice and easy. If I take the other one, now the other one has got the masses at the outside. If I want to rotate that, that's much harder. It's more reluctant to me changing its motion. Remember there was a word we used for reluctance, for something to change its motion? That word was inertia. Hopefully you met the word inertia back in 4th year. And when we spoke about inertia in 4th year, what we said was a big mass is difficult to get moving and difficult to stop moving. So if it's got a big mass, it's got a big inertia. It's reluctant to change its motion. Now we don't talk about inertia very much because we talk about mass. Mass is measured in kilograms. The bigger the mass, the harder it is to get it moving, the harder it is to stop it moving, the harder it is to change its motion. You need a bigger force to get it to accelerate. So mass and inertia are directly proportional to each other when you're moving in a straight line. The bigger the mass, the more inertia it has. The more reluctant it is to change its motion. These 2 rods have got exactly the same mass, but this one is dead easy to move. To rotate, this one is much harder to rotate. I need a bigger turning force to be able to get this one to change its motion. I need a bigger torque to be able to give this one an angular acceleration. So, easy, difficult. Oh, that's tough. I don't know if you've ever seen a tightrope walker, but a tightrope walker will often walk with a big long rod, and the reason for that is that it makes it easier for them to keep their balance, because this big long rod is reluctant to change its motion. Now, the name that we give to the reluctance of an object to change its angular motion is its moment of inertia. Why is this one harder to move? Even though they've both got exactly the same mass, why is this one harder to move? It's because the mass is further away from its axis of rotation. So, the reluctance of a body to change its angular motion depends not just on its mass, but how that mass is distributed, how far away it is from the axis of rotation. The bigger the mass is, the more inertia it's got. But the further that mass is distributed from the centre, the more reluctance it's got to change its motion. And the combination of the two of them, the mass and the radius of its rotational motion, the two of them combined gives us a quantity called the moment of inertia. So let's see this on paper then. Remember in fourth year when you did F equals ma, Newton's second law, we spoke about how you need an unbalanced force to accelerate a mass. Now, every particle in that mass is all doing the same thing. You need a bigger force to accelerate a bigger mass. But it's a different story for rotational motion, because in rotational motion, the particles are all moving at different speeds. So in linear motion, all the particles are moving at the same speed. If it's accelerating, they've all got the same acceleration. If I was to draw all the little particles in that mass, then if you exert a force on it, all the particles do exactly the same thing. F equals ma. In a circle though, in circular motion or rotational motion, the further a particle is from the centre, from the axis of rotation, then the faster its tangential speed will be. Particle B is travelling faster than particle A because it travels a greater distance in the same time that it takes for particle A to make one revolution. So, if these particles are travelling at different speeds, depending on the radius that they are from the centre, then we have to derive a new quantity that will allow us to deal with the mass or the inertia of a rotating object. Now we start off with Newton's second law. That's going to be our starting position. So let's think about that. If we want to make an object rotate, well, we've already derived our equation for the force that's providing a turning effect. That's a torque. So the torque, the turning effect, is the force that you apply at right angles to the radius of your circle. And we've also got a relationship about angular acceleration from your relationship sheet. The linear acceleration is the angular acceleration times the radius. Now, if we take F equals ma and multiply both sides by r, we get Fr equals mar. And then we substitute in for A equals alpha r, so that we now have our angular acceleration on the right hand side. Fr is the torque. And if we gather the terms on the right hand side, if you notice that we have an r times an r, that gives us an r squared. If we gather the m and the r squared together, we now have an equation that looks very similar to F equals ma, where the torque is the turning force, alpha is the angular acceleration, and mr squared is a rotational equivalent of mass. It's called the moment of inertia of a particle that is in a rotating object. There's the equation for it. Now it's got a symbol I for inertia. And the units of moment of inertia, if we just look at the equation, it's mass times radius squared. So it's kilograms times metre squared. Kilogram metre squared. So our rotational equivalent of Newton's second law is that torque equals moment of inertia times the angular acceleration. Tau equals I alpha. That's the equivalent of F equals ma for rotational motion. So moment of inertia depends on the mass of your object, but also the distribution of the mass of the object. Now, different shapes will have different distributions of masses within them. and you will only meet a certain number of shapes in advanced higher physics. And you will find the moment of inertia of those shapes in your relationship sheet. So here's the most current version. And here's what we've covered so far. Linear equations of motion. We've covered angular motion. There's an awful lot in there. All the way down, we've now got radial acceleration and centripetal force. Underneath that, you will see moment of inertia, torque, and angular acceleration. And I'm going to draw a line there because underneath is angular momentum, which we will cover later. In the meantime, though, check this wee guy out. That symbol means the sum. And it's the sum of all the individual particles in a solid object. It's the sum of all the moment of inertias of the particles in a solid object. How the heck do we work that out? Well, you don't need to. Because the sum of all the individual moment of inertias of the particles within solid objects, the ones that you are going to meet, is given at the back of the relationships booklet. Now, it's a hefty booklet in advanced higher, 8 pages or whatever. If you scroll down, we've got the Unit 2 and Unit 3 equations. You've then got a whole page of higher equations, but keep going and you get to a page of additional relationships. Things there like the geometry of a circle, there's trig identities, there are tables of standard derivatives and integrals, but also on that page, if you scroll down to the bottom, you will see moment of inertia. Strange place for them to be. But these are the mathematical, calculus-derived relationships for solid objects. Let's look at them 1, 2, 3, 4, 5 of them there. Let's look at them one at a time. First one, a point mass. So the moment of inertia of a point mass, which is, as its name suggests, it's a small mass located at a single point that's being whirled around in a circle. Its moment of inertia is mr squared. So that's a point mass. A rod about its centre is a solid rod that's rotating about its midpoint. A rod about its end might be like a spoke on a bicycle wheel, where one end is fixed at the centre of a circle. And you might have a number of spokes on a wheel and you would add them all together to get the total moment of inertia. It's worth noting here about a hoop, like the rim of a bicycle wheel. In a hoop, all the mass is at a fixed radius. So all the individual particles, the sum, if you like, of all the individual particles, the total mass is at that fixed radius. So if we added up all the sum of all the masses, they're all at the same radius. And sometimes you'll see that equation replaced with a capital M, because the total mass is at a fixed radius for a hoop. A disc about its centre might be a solid flat cylinder. Its moment of inertia is a half mr squared, because the mass is distributed between the centre and the maximum radius. So a half mr squared. And the last one that you might meet is the moment of inertia of a sphere about its centre. It might be a ball rolling down a slope, or it might be a planet spinning on its axis. 2/5 mr squared. There are, of course, loads of other shapes with their own moment of inertias, but these are the ones you should be familiar with. They're in the relationship sheet. Make sure you have your own personal copy. There's one in Google Classroom, and there's one on the school website. That's it.